The roar of engines slowly swells beneath the soundscape until archival footage replaces the ocean. Aircraft carriers at full steam, mechanics rushing across metal decks, pilots tightening harnesses before launching into the sky. The narrator enters with a calm and authoritative tone, explaining that while the world remembers the Pacific War as a violent clash of fleets, islands, and nations, another war unfolded far from the public eye. It was a war fought not with bullets or bombs, but with pistons, turbines, fuel mixtures, and superchargers. A silent technological arms race that would determine which side controlled the skies. This lesser-known conflict would later be called the Secret Engine War between Japan and the United States. Long before Pearl Harbor, Japan and America had already embraced radically different philosophies of flight. Japanese strategists envisioned aircraft that could roam vast distances across open ocean, strike with precision, and maneuver with fluid grace. This mindset shaped the early design of the Mitsubishi A6M0, powered by the lightweight Nakajima Sakai radial engine. The Zero became a marvel of range and agility, built with almost ascetic minimalism, stripped of significant armor, light enough to dance in the air, and deadly when in the hands of experienced pilots. Meanwhile, American engineers at Pratt & Whitney and Wright were pursuing a different ideal. Their engines were heavier, more robust, and designed for durability under intense combat stresses. The idea was simple: build engines that could survive dives, high-G maneuvers, hostile weather, and enemy bullets. American airframes shaped around these engines were built like muscular athletes, strong, fast, and resilient. When the Zero first appeared in the skies after the attack on Pearl Harbor, many American pilots felt as if they were confronting a supernatural machine. Early in the war, the Zero's astonishing maneuverability in long range allowed Japanese pilots to dominate the air with kill ratios no one in Washington believed at first. But this dominance came from carefully chosen compromises. Its engine was compact, reliable, and efficient, but the airframe around it sacrificed armor, self-sealing tanks, and even structural reinforcement in exchange for performance. One of the turning points in understanding the Zero happened by accident. In June 1942, a Japanese pilot crash-landed on Akutan Island in the Aleutians. The aircraft remained almost perfectly intact. American salvage teams recovered it, repaired it, and secretly flew it. This Akutan Zero became something of a mechanical Rosetta Stone. By testing it relentlessly, American pilots and engineers learned exactly how the Sakai engine delivered its performance, and what limitations the Japanese designers had chosen to accept. They discovered the Zero's weaknesses in high-speed dives, its sluggish roll rate at top speed, and its structural fragility under extreme stress. These findings, combined with battlefield experience, helped the United States rewrite dogfighting tactics across the Pacific. Instead of engaging in turning duels, American pilots began to use energy-fighting maneuvers, diving attacks, and rapid disengagement, tactics that leveraged the greater horsepower and ruggedness of American engines. Meanwhile, back in the US, an engineering revolution was underway. In factories filled with deafening noise, the Pratt & Whitney R2800 Double Wasp, a massive 18-cylinder radial, was being perfected. This powerhouse engine would drive the F-6F Hellcat, F-4U Corsair, and P-47 Thunderbolt aircraft that would ultimately dominate Pacific airspace. These engines were brutal in output, often exceeding 2,000 horsepower, and their airframes were built to channel this power into speed, climb, and lethality. They gave American pilots not just a fighting chance, but a decisive technological edge. As the war progressed, Japan's engine industry came under severe strain. Limited access to high-grade metals, smaller industrial capacity, and relentless damage from American bombing forced engineers to push existing engines far beyond intended limits. They experimented with water methanol injection, emergency boost systems, and high-altitude supercharging. But every improvement created new problems: overheating, maintenance difficulties, and inconsistent reliability. Then came the B-29 Superfortress. Driven by four massive Wright R3350 duplex Cyclone engines, the B-29 represented a new level of high-altitude strategic capability. But the R3350 was temperamental and dangerous. Overheating could cause engines to ignite. Mid-flight, an entire aircraft were lost before engineers redesigned crucial components. On the ground, technicians waged a technical war entirely separate from the dogfights happening thousands of miles away. Their victories, small changes in cooling, airflow, or ignition timing, directly enabled the bombing campaigns that devastated Japan's industrial infrastructure. One of the B-29's most symbolic targets was the Nakajima engine factory at Musashino, the heart of Japan's aircraft power plant production. Destroying it meant grounding future fighters before they even existed. Japan struggled to replace lost engines, and the decline in available power plants began to cripple its ability to field competitive aircraft. By 1944, the question was no longer which nation had the best engine on paper, but which could sustain a massive, uninterrupted supply of reliable engines while under immense wartime pressure. Yet in the war's final months, both nations turned their eyes toward the future, the jet age. In the United States, Lockheed engineers under Kelly Johnson raced to complete the P-80 Shooting Star, the first operational American jet fighter. Though it arrived too late to see combat, it represented the American leap from piston technology into turbine-driven aviation. Japan, under bombing and material shortages, managed to produce its own pioneering turbojet engine, the Ishikawajima Ni-20, based on limited intelligence about German designs. The resulting aircraft, the Nakajima Kika, made its first flight in August 1945, just days before the war ended. The Kika was a testament to the skill and determination of Japanese engineers, but it was a technical achievement born too late to alter history. When the conflict finally ended, the remnants of the secret engine war settled into silence. Radial engines gave way to jets, and nations rebuilt their industries. American aviation surged into the jet and space age, while Japan, prohibited from developing offensive aircraft, poured its engineering talent into civilian industries, automobiles, electronics, and later global aviation collaboration. Ironically, the precision, discipline, and mechanical expertise that once powered wartime innovation soon powered peaceful technological revolutions. The secret engine war between Japan and the United States remains one of the least visible yet most decisive battlegrounds of World War II. It illustrates that in war, the defining victories often come not from dramatic battles, but from laboratories, factories, and design tables. It tells the story of thousands of unseen contributors whose hands shaped pistons, forged alloys, and calibrated fuel injectors. Their quiet struggle, measured in horsepower, heat, altitude, and reliability, determined who would rule the skies and ultimately who would shape the future of aviation.